Before introducing our next speaker, I would like just to mention that we are recording all the plenary talks, and then they will be uploaded, hopefully, on the Ifac YouTube channel. So in case you can just watch them back when you're at home, just in case you're missing something. And of course, we'll try to secure the PDF files from our speakers and post them on the website. Okay. Having said this, I would like to introduce our next speaker. It's my pleasure to introduce Professor Lacra Pavel. Lacra received her degree of engineer in automation and computers in 1989 from the Technical University of Iași in Romania. And then later on she moved to Canada, where she got a PhD at Queen's University, sorry, in Kingston. And since 1992, she has been a faculty at the Department of Electrical and Computer Engineering at the University of Toronto, where she is currently a professor. Her main research interests are at the intersection of control, optimization, and game theory. And I think the contents of her plenary will be about this. Okay. Lacra, the floor is yours.
Thank you very much, Claudio. And thank you, Min, for inviting me. I'm very happy to be here. I've traveled quite a long way, but I have to say that it's very worthwhile. This is a very beautiful old university city, and I've enjoyed walking around. I actually read it's been in service since 1614, which is quite a long time ago. So it's one of the old universities in Europe. I hope that my talk is not going to be one of those that you go and replay on YouTube just before going to bed. This is just to make the connection. What I'm going to talk to you about is on the extension of Nash's game theory to networks, and it's mainly focused on the type of work that we've been doing in our group on this topic. It's based on joint work with two of my PhD students, Diana Jov and Farzad Salehi, and one of my postdoc, Peng Yi. So the motivation is presented by the networks that are all around us. And what you see there are two such examples. Social networks, obviously, it has to be there. And then the wireless ad-hoc networks, which is, again, a very representative example of the scenarios that we're looking at. Before getting into game theory for networks, or network games, as we want to call them, I'm going to actually go into presenting a little bit of more of a tutorial nature of game theory, knowing that this is a workshop focused on distributed estimation and control. I thought that this would be a good way of getting there. So first of all, what's a game? So we're assuming that we have a number of players or agents, as everybody's familiar with, two or more, or decision makers. Each has either a finite number of choices or a continuum of choices, and we call these actions or decisions. At the end of the game, there is some payoff to be gained or some cost to be paid by each player. So if in standard optimization we have a single decision maker that typically optimizes an aggregate common objective or goal, in a game there are multiple such decision makers. We call them self-interest players or agents with their own goals. So to put it in a formal way, we denote the V as the set of n players, and each player I has that action denoted by x sub I, selected from his action set, omega I. And that could be finite or continuous. And this leads to the type of finite action games or continuous kernel games. Each has an individual payoff or utility, U, capital UI, or a cost function, J sub I. And he takes an action to maximize his own payoff or minimize his own cost. or the expected value of that. The key is that his success in making those decisions depends on the actions of the others or the decisions of the others. So that's why we denote the cost. I'm going to mostly talk about cost being equivalent to the utility. You see there is a function of x, where x is the action profile of all the other ones. So we're going to denote that x as a pair, x sub I and x minus I, where x minus I denote the actions of everybody else except player I. So that coupling is evident in the cost. And we're going to denote such a game by the triplet script G. And we all know that this subject or this topic of game theory handles the strategic interaction among such multiple decision makers and provides the mathematical framework of analyzing it. We're going to say that a player is rational if he makes choices that optimize his expected utility. Yeah. And in terms of a solution concept, there could be different solution concept. And one of the most intuitive is what's called the security strategy. And that says that a strategy is called a security strategy when you're minimizing the worst possible cost or the maximum cost. And the minimax solution is when each of the players uses such a security strategy. One of the well-known examples is the prisoner's dilemma game, where there's those two prisoners put in two cells, and they have the two choices, either to confess or not confess. And the cost that each is going to incur as a result of that decision is depicted by that matrix M that has the two elements. First represents the cost for player 1, second for player 2. So the player 1 is going to pick one of the rows, player 2 one of the columns, and it turns out that confess is the security strategy for either players. When one looks and evaluates what's the worst possible cost that I'm going to get, for player 1 you're going to see that is going to be the first element 5, 0 or 15, 1. So obviously he's going to get the less if he picks the first row. Same if you look at the second element, and player 2 is going to say the worst that I'm going to minimize is going to actually lead me to also to confess. So this leads to the minimax solution to be the element that is in the confess, which gives them both 5 years in prison. And you can see that they can either have the incentive, oh, should I maybe not confess? But obviously this gets into the second type of a solution. And this has to do with what's called a best response. And this is a strategy where each plays an action that gives the best possible cost given what the other player does. So we're going to say that given that his opponents play x minus I, a best response strategy for player I is that x sub I star, such that he's minimizing his cost given that opponents play. We call a Nash equilibrium solution when everybody uses a best response. So that's represented by that inequality that now has to hold for every player I. And it is an n-tuple. This is a strategy profile. And essentially, it's a strategy profile that's at the intersection of all best responses. What's so nice about it? Why is it called Nash equilibrium? Well, the key is that by the definition, no player has any incentive to deviate from it unilaterally if the other ones do not move. So this is what's called the no regret. In this sense, we might expect that a set of rational agents are going to choose an equilibrium solution. And this is the most famous equilibrium solution that game theory is concerned with. How do we characterize games so that, first of all, they do have an equilibrium solution? Secondly, how do we devise algorithms or dynamics for the players to follow such that when they update their actions or decisions, they're arriving at a Nash equilibrium? Back to the prisoner's dilemma game, it turns out that confess is in fact the unique Nash equilibrium. If one goes through the choices and evaluates, what if I knew what my other player, my opponent was taken? Would I be possible to get a better cost in the sense of testing that no regret hypothesis? If you go through the motions and check and assume, okay, I'm player 1. And let me just say, what if I knew that player 2 pick the confess? Could I have actually done better if I chose a different action, unilaterally deviating? If I knew that he's picking confess, which means column 1, no, I don't have any way of actually regretting, because my other choice would be row 2, or not confess, which gives me 15 years in prison. So he doesn't regret. And same for the other one. Another famous game, matching pennies. The flip coin that we all know about. Well, it turns out that this game does not have an equilibrium solution. However, if one thinks about randomizing choices, not necessarily picking an action or the other, but maybe picking it with a certain probability, then it turns out that this game has an equilibrium solution in mixed strategy or randomized strategies. And von Neumann proved since 1922 that every two-player zero-sum game has an equilibrium in mixed strategies. And he did it by using geometric arguments. It took 20 years for Nash to actually extend this result to n-player finite action games. And he proved that every n-player game with finite actions has an equilibrium in mixed strategies. And he made use of one of the fixed point theorems, either Brewer's or Kakutani's fixed point theorems. Finally, moving to continuous kernel games, so the case in which that omega I is not a finite set, but it's a continuous action set, de Breuil, Glicksberg, and Fan simultaneously almost extended this result to continuous kernel games under conditions that are reasonable on the action set being non-empty, compact, and convex, and cost function being continuous jointly in the actions and convex in the action themselves of each of the players. So you see that convexity in xi. And what's nice is that every such game has a pure Nash equilibrium in the sense of in actions or in decisions. We don't need to do that randomization. And this is actually the setting in which I'm going to place most of my talk that follows. But this is so that you see what is it that laid the foundation of game theory. So the classical setting originating and is used in economics and social sciences, and it relies on this equilibrium analysis, the type of the analysis that we did based on Nash equilibria or its refinements in case you have multiple such equilibria. It offers traditional explanation as to when and why an NE arises, and typically it's focused on one-shot games. In other words, players interact only for a single run. What's more important is that such an NE, a Nash equilibrium, is typically understood to arise from analysis and introspection from sophisticated players that actually have common knowledge about the game. You saw that complete information that they had to have that type of a payoff matrix based on which to make their decision. And this is what we call complete information. Well, the alternative justification is what's the subject of learning game theory, and this is more relevant for our engineering or social systems. A repeated game, first of all, where players interact continuously for multiple rounds of the same game. And it is understood or hoped that the Nash equilibrium will arise as a limit point of such repeated play in which maybe less than fully rational players update their behavior, their actions, based on the interactions with the other ones. Again, the information that's available to every such player is critical. This is the setup. In terms of what kind of learning? Well, they could be the most common and the most used and the most studied is what's called the myopic learning, or simple rule of thumb type of learning with no forecasting. Examples: best response, the same type of update that you saw in the definition of a best response mapping. Basically, every player uses a best response, computes a best response to what the other ones are doing. Fictitious play, it's the same as best response, except that instead of a strategy, one player uses empirical distribution as an approximation of the strategy of the other players, because again, he needs that information. Then a better response or a gradient play could be another type of play where, again, he needs to know what the other ones are doing. or in the class of reinforcement learning. And this is where that less than fully rational type of players, where players only use the payoff-based value after each iteration of the game. In evolutionary games, another type of scenario is where players select strategies based on their performance against aggregates or random mutations. So this is an area that has been quite developing. Now, in terms of network games, and this is where we're going to place ourselves, the setup is this multi-agent system or networks that we're all familiar with. And it presents complex problems. Multiple entities that could have individual goals and capacity to act in the presence of limited resources and possible central controller issues. Applications range from transportation, communication, economics, social networks. Again, the major challenge is how do you enforce that coordination between the agents, considering what information they do have. Now, there has been quite a lot of work, we could say since about 2000, 2001. You see there a number of areas ranging from congestion control, power allocation, communication networks, mobile sensors, resource allocation in cloud computation, demand response management in smart grids. And important strides have been made in actually developing such algorithms or dynamics that operate in each of these scenarios. And people have typically used the specifics of that particular problem setting to advance it. They consider the players or the agents being either the network nodes or the routers, the channels or the robots or the network users themselves. And the key was that they were sharing a common resource, bandwidth, power, capacity. Different approaches have been taken, continuous kernel games or finite action games, evolutionary games. Despite all of this, there isn't as yet a unified theory for games on networks or over networks or network games, whatever name you want to give to it. So the idea is that you'd like to get to a distributed type of algorithm that's allowing the agents to learn about the others and the game. But there are challenges. There's this complexity of network interaction among the agents. They only might have local or partial information. That information could be obtained as delayed or asynchronous communication. The environment is non-stationary because once they learn about the other agents, their other agents are learning themselves. And all of this is actually bringing to mind the two other areas that are related. One is multi-agent consensus or agreement. They also have a set of agents that, moreover, are typically assumed to be dynamic, but generally decoupled agents, where they might have properties individual to themselves, and where typically an objective of the type of consensus of the internal states or agreement of the outputs, of synchronization. This is the typical objective that's enforced. And one is looking for algorithms or dynamics that are distributed and allow all of them to achieve that objective. And this translates in a quadratic objective type of function. What's important is that those individual properties, I put their incremental passivity or convexity, are typically assumed for each of those agents. And we're going to see that this is not something that a game framework allows or typically has, unless the game is very simple. And then the other one is distributed optimization. There again you have, and you've seen this this morning, the setup where there's a set of players that all of them cooperate towards optimizing some objective, some common or aggregated objective. And each agent optimizes only part of it. The difference from a game setup is that in this case, that separation and the fact that each agent has full control over the argument of the part that's optimizing leads to, maybe after a few steps, a type of decoupled problems. In a game setting, on the other hand, each agent optimizes their own objective, so does not cooperate towards a bigger goal or common goal, and has authority only over his own actions. But his objective depends on what the other ones are doing. So he does not have full authority of whatever argument I have there. This translates in coupled problems with incomplete authority over the full argument. And this is technically one of the biggest challenges that I see as distinguishing game theory from network. If one would have a game setting, and there are nevertheless a variety of cases in which the cost functions themselves are what we call separable. They're decoupled one or another. And maybe you have coupling only in the action set. Let's say the actions have to be, the sum has to be less than something. In this case, it's translating into very much something that looks like a distributed optimization problem. But that's a very special type of a game. The most general one is the one in which you have this full couple. So this is the setting. I've represented there the schematic of a network that you might have, the players. So this could be, for example, those players that were playing the matching pennies or the prisoner's dilemma, whatever it is. The fact that each has an individual cost that depends on the others could be represented by that interference graph that you see at the top there, where the edges represent the possible interdependence of the cost functions of the agents. And then we have a second graph that we call the communication graph, where the edges describe the ability of two agents to actually get information from one to another. And remember that we said that in the beginning that that important concept of a best response solution was dependent on what the other ones were doing. So somehow, if you have a network with 100 players, given Professor Morse's example this morning, if it's a game that depends on all of you in this amphitheater, if my payoff depends on all of you, I should be able to know the actions of all of you. But maybe I cannot see what every one of you is doing. Maybe I can only see whatever those close to me are doing. And this is what that communication graph is describing. They could be identical or not, complete or sparsely connected, directed or undirected, static or time varying. And this is the whole setup. So when one attempts to do it, it turns out that what's useful to use are tools from convex optimization, graph theory, monotone operator theory, multi-agent dynamical systems and control. So that's where that intersection, and that's why I'm interested in this area. This setup has actually, in its generality, has started to be looked upon quite recently. So the first bullet there typically assumed a central node authority. What does this mean? It means that whatever information I needed about all of you, there was some central coordinator that was able to provide it to me. In this sense, the work that has been done, and Fakine and Pang have quite an extensive treatise, and then a lot of other works, Parisi and the others in the setup of aggregative games, assume that the interference graph is complete, and that communication graph is a star. The node, the central node, is that coordinator. And then center free has started to be, again, being developed. The first was Nedic, Angelia and Udai's CDC paper, aggregative game with an incomplete communication graph. And I remember talking to Angelia afterwards, and I said, wow, that's such a nice result, Angelia, and it makes such a nice parallel to what people are doing in distributed optimization. I said, are you aware of anything that's in the general case? Because what they were treating the case where the coupling, remember that I said that simplest case is when each cost depends on only his own action. They were treating the case in which the cost depends on their own action plus a scalar variable that aggregates everybody's else. So their approach was, let's just try and estimate that aggregate scalar variable by using a consensus type of algorithm. And I thought that's a beautiful idea. And then Bachman and Jorge had another very nice work on two network of players playing a zero-sum game, where again they were trying to actually learn about the other ones by communicating over a graph. In this particular case of zero-sum game, again, we thought this is again a very important. I put them there because I think these are some of the earliest type of results. Then Zoom-Frazzoli actually treated the case in which the interference is partial, but which means that my cost depends on only some of you, but I can actually see what all those some of you are. And this is what I call communication graph is the same identical as the interference graph. So we started from this, and basically we've developed some results for general coupled games, monotone, under complete or partial interference graph for incomplete communication graph. And that GC, you see, it's a part of the interference graph. And this has been, CDC was 2014, so 2 years after Angelia. But in Automatica, it appeared first in 2016. So I'm going to talk a bit about this setting. So we have there the set of players and the cost function. And then the interference graph, you could have those choices. Remember that I said it could be complete, partial, undirected, complete but directed, or partial and undirected. And the communication graph in all of this is partial, and it's a subset of that interference graph. So the problem is, how would one devise an algorithm to actually get to a Nash Equilibria under this limited or partial information scenario? The assumptions, first of all, connected and undirected communication graph, and this is going to be the most scenario that I'm going to talk about. And then some assumptions that are typical. You saw for existence of a Nash Equilibria, compact and convex action sets, jointly continuous cost function, convex only in their own individual action, and then some extra assumptions on the pseudo gradient. What you see there are the partial gradients of each of the cost function with respect to their own action stacked together. So this is not a true gradient. And those monotonicity assumptions could be either strictly monotone or strongly monotone, basically both of them ensuring that I have a unique Nash Equilibria. And there are results even for monotone only, in which case you could have multiple Nash Equilibria. The key is that this monotonicity takes the place of the convexity that one considers for the aggregate cost function in distributed optimization. What I made there as a note, and I think is very important, is the fact that the pseudo gradient being monotone, it's actually translating into it being as a static map, an incrementally passive map, or an equilibrium-independent passive map. And this is one of the nice observations that allows one to make the connection between this whole setup of game theory and multi-agent dynamical systems. So in this setup, the objective is to design a distributed algorithm to find a VNE using only partial information over that communication graph that is not the full interference one. So one starts with the characterization. Well, we know that the Nash Equilibria lies at the intersection of all best response maps. We've seen that in the tutorial type of first part. And this is shown in that picture over there as at the intersection of the two-player game best response map. So we can see that as a fixed point of the overall best response map. Alternatively, one can characterize this Nash Equilibria via variational inequality for the pseudo-gradient. And that VI that you see over there, or translating in a monotone inclusion, where n sub omega is the normal cone. Again, a fixed point iteration translates into that FP relation that you see there for all players. And this is actually the starting point based on which one can actually develop iterative algorithms or dynamics to converge to a Nash equilibrium. The key, you see there that fixed point assumes that you know all of the others' actions. So perfect decision information. So I'm going to just present the standard type of algorithms or dynamics in this perfect information. What does it mean? It means that agent instantaneously observe what all the other ones are doing. It's like I have a complete graph with every one of you. And if I use at each iteration an update as in 1, where basically I'm using that relationship, what does it mean? It means that I'm taking a step that uses my partial gradient with respect to my own action with some step size alpha. And I'm projecting that P sub omega is projecting on my action set. And if everyone does it, and then you stack it in compact form as in 2, turns out that under strong or strict monotonicity on Lipschitz continuity of the pseudo-gradient, such an iterative algorithm converges to DNE with either diminishing or constant step sizes. And it's been shown by Ifac and Ifac. The key there is you see that x minus I in 1 there. So this is what shows you that I need that information. So one can actually recognize that one can think in terms of continuous time dynamics, starting from this. So if one uses the property of the projection that it's the resultant of the normal cone, then one could get to an alternative continuous time differential inclusion, or as in 3 as a projected dynamical system, where this time the right-hand side is not necessarily Lipschitz. So that 3 is actually represented as that block diagram that you see over there. And why is this nice? Is because what you have on the forward path is an integrator, a stack of integrators. What you have on the feedback path, you have, first of all, feedback of all of the actions through projection of the pseudo-gradient. And we all know that interconnection of passive system leads to a passive system, and we can use it to derive convergence or asymptotic stability. Exactly the same principle stands here because those integrators being passive. If I have the feedback path passive or incrementally passive, and that stands if my F is monotone, then I have convergence, which is quite beautiful. So now moving on to partial information case over this graph GC. Now, we are only assuming that each knows their own cost function, their own action set, does not know all of the other ones, but maybe he can get it from his neighbors. So we're going to assume that there is no central node that disseminates that information, as in the central node scenario. What's the idea? So the idea is that each is going to build an estimate of what the other ones are doing by communicating with their neighbors. And that estimate is denoted by that bold X superscript I minus I. In other words, player 1, top left. He's going to have his estimate of all the other ones denoted by X1 minus 1, which encapsulates what the actions of our player 2, 3, and 4 are. Player 3 is going to have X3 minus 3, which encapsulates what player 2, 1, and 4 do. So basically, everyone has to have this estimate of all the other ones. Ideally, all of these should be the same. So that's where your idea of consensus comes. So we all know the typical consensus problem where there are n agents, each with a different variable, marked a different color, and if they communicate locally over a partial graph that's connected, if they update iteratively those actions, they all get eventually to a consensus. So the same color of balls. In a game scenario, you actually have each having an n tuple. So you see that displayed as the left column, that n tuples have different color frequencies or proportions. The hope is that after doing communication, they should all get to the same proportion of colors, which means that those n tuples are the same. So that was our idea. Combine consensus on what the other ones are doing with a projected gradient so that they eventually converge to the Nash equilibrium. And again, we've started from Angelia's and Udai's idea, where in their case, they were only estimating that aggregate variable. Here we said, well, in general, they have to estimate what all the other ones are doing. So the first asynchronous gossip-based algorithm we developed is inspired by this, where each of the players is actually interacting with their neighbors in a gossiping sense. So they're averaging at each step when they wake up with what the neighbors does. In the local step, they're going to use basically a projected gradient, the same type of an algorithm, where instead of x minus I, they use what's in that green bubble, which is the estimate of what the other ones are doing, based on the way he's computing it. So it's nothing more. It turns out that under strict monotone and Lipschitz pseudogradient with diminishing step sizes, we can show that these estimates converge to the consensus, and the actions of all of the players converge almost surely to the Nash equilibria. And this is based on a super martingale type of a result. And further on, we've extended and we've shown that this could be extended to a complete or sparse interference graph, directed or undirected communication graph, by just modifying appropriately step 1 of gossiping. Well, this is all very nice. It turns out it's very slow. This diminishing step size idea, it's been something that has been bugging me personally, if I can say so, because I've always felt that, first of all, there has to be a way in which one could get around. The fact is that for constant step size, we could not show convergence, exact convergence. We always had just a neighborhood of the Nash equilibria, and that's it. And then, in fact, when one thinks to a continuous time parallel, this is almost as if you have a 2-time scale system. Fast consensus, slow projected gradient. And somehow, there has to be a way in which one could actually do that on a single time scale by maybe use some correction term. Because remember, what we've used was nothing more than just the same way in which the algorithm was. Projected gradient, except that I'm replacing the estimate instead of the true actions. So this is what 2 types of approaches led us to. The first one is a continuous time, single time scale, via passivity and multi-agent agreement. So the same game scenario where they're all interacting over an undirected communication graph. Our hope is to design a new continuous time projected gradient dynamics, single time scale such that it converges to a Nash equilibrium. Same idea, endow each of the player with an estimate, the state of what the other ones are doing. And we want to exploit passivity and monotonicity such that these state vectors achieve consensus and converge to the Nash equilibria. So you have what's, in fact, like a multi-agent agreement problem. And the solution we came up with is displayed at the top there. So what you see is that the first line is the component of the action. It's a projected gradient type. You see that the partial gradient plus a correction. And that correction is through the Laplacian, depending on what the other neighbors are doing. And then the second component is the component on the estimates for what the other ones are doing. That's only involving the Laplacian. So it looks like a multi-agent agreement. What's different? Well, it's technically, remember that I said that a lot of these differences are technical. In standard multi-agent agreement, the dynamics of the agents are, first of all, decoupled one from another. They could be heterogeneous, but they're decoupled. So if one just erases that Laplacian addition from both components, I can say that if I take x super I as the state variable, I have decoupled heterogeneous dynamics. It's fine. Well, the other typical assumption in multi-agent synchronization is incremental passivity individually for each agent. And in this sense, this would translate in individual monotonicity of each cost function with respect to the full argument. But that's not what I have in a game setup. It's only in a distributed optimization where, because of that separability, I can actually claim that. So this is the big challenge, and then you have that projection over there. Nevertheless, if one stacks this compactly, one gets what's there in 4. So it's a projected dynamical system, and now what's involved, it's an extended pseudogradient, that bold F there. Bold F, it's now defined on the full augmented or lifted state space. All of the agents' states or estimates of all the other ones. It's omega to the n. It still takes values in Rn. So it's only as if I'm evaluating the pseudogradient at the estimates. So it turns out that if one assumes a monotonicity assumption of this extended pseudogradient, then one could essentially use an argument as in multi-agent synchronization, interconnection, and so on. We actually wanted to relax this because it turns out that it's quite hard to get to a condition where you do have monotonicity on an estimate on the extended space. So the way in which we were able so far is to actually assume only Lipschitz continuity. And this is a definitely milder assumption. So definitely if I'm looking at quadratic games, this is automatically assumed. True, yeah. So under this Lipschitz assumption, if I now look in block diagram form, this is how it looks like. So I have a stack of integrators in terms of the full states, actions and estimates. And I have feedback involving that projected extended gradient. And an extra Laplacian feedback that actually is providing me that correction. So this is the block diagram that actually allows us to actually prove convergence. So what's the idea? The idea was that we're going to decompose that augmented space or the lifted state space into a consensus subspace. And it's orthogonal complement. The consensus subspace is where I would like to get. So if one then takes this extended pseudogradient and decomposes it, one can get a consensus term that's the green one, and then off consensus term. The consensus term, one could use properties of my original pseudogradient. Why? Because there it just boils down to the original. And then off the consensus space, I can actually use properties that the Laplacian has. The Laplacian, I know that is actually a strongly monotone on the orthogonal complement because of properties of my L matrix that's doubly stochastic. So by balancing the shortage of passivity that extended F has with this excess of passivity that the Laplacian has, we are able to actually prove under standard, strongly monotone for the original gradient and Lipschitz, that if the second smallest eigenvalue of the Laplacian satisfies some inequality related to the strength of the coupling in my game, then any solution of that dynamics converges single timescale to the Nash equilibria asymptotically. And that picture actually denotes what one has, because essentially what this is doing is that it shows you how the effect of the Laplacian is to bring the dynamics closer to the consensus subspace, where the projected gradient component is actually taking it to the Nash equilibria. So this is actually some work that we've presented last year at CDC, and it's going to appear in TAC. I think it appeared online already. So this was the first type of a result. And in block diagram, I wanted to actually put it here just so that one could see the parallels to a distributed optimization setup or a coordination type multi-agent setup. Because what do you have there? You have that block diagonal from the integrators. And then you have the coupling that's appearing through the extended pseudogradient at the top there. Then R and S are matrices that essentially extract the actions and the estimates from the full state vector. And this is showing nicely both the similarities and the differences versus a distributed optimization problem, because in a distributed optimization problem, even the top block would be a diagonal, would be decoupled. The second approach was, again, thinking of this parallel to which problems that people had in distributed optimization with using diminishing step sizes could be overcome by maybe using something that is like acting like a correction. And ADMM is one of the most used approaches. So what we've actually exploited here is this similarity, where the Nash equilibria problem is shown as in 1. Each aims to minimize their own costs subject to the action being in the action set. The moment in which I'm introducing the estimate of all the others, I get to that X super I, local copy. So the problem is like as if I had a modified game in terms of minimizing AI, but subject to some virtual constraints with my neighbors. So one can think of then, maybe I can get to an ADMM type of a method so that I get an algorithm that can operate on a single time scale or with constant step sizes. We do the same thing. We're introducing an extra variable to separate those virtual constraints, and we introduce an augmented Lagrangian, L sub I. The difference is that, again, you have this coupling in J sub I that a distributed optimization problem does not have. The moment in which you're extending it, those individual problems for each agent they are decoupled one from another. The type of algorithm that one gets after following an inexact type of an ADMM approach is displayed in these 3 steps, where one is the dual multiplier that basically takes care of the Lagrangian multipliers of each player. And you see there that you have the type of only local information update being true. And then the middle one is what's the action update. It's again a projected gradient method with a correction term. So you see here that now you have that Laplacian, like that's the last one, and then you have also the Lagrangian multiplier appearing there. And the last one is for the estimates, again, based on a Laplacian-like. Similarly, we can show that under a co-coercivity assumption of the extended pseudogradient, for sufficient constant step sizes related to game coupling and connectivity strength, we can show convergence in a single timescale with constant step sizes. So something that we weren't able to show with the first type of an algorithm that we proposed just based on gossip. Exact convergence to the Nash equilibria. So now I'm going to basically just show you a few of the examples. First example is this economic game example where you have a market and a number of suppliers that try to access different markets, and each is trying to maximize their own profit. But the total quantity produced is what determines the price. And obviously, different actions from the other firms influence what one gets as a profit. For the type of quadratic cost function and the type of a linear production cost and the linear demand price, if one considers 20 players, one could run the type of dynamics, projected gradient with correction, over a random communication graph. So what you see to the left is typically a random communication graph that we assume. And one can show that the steady state value is the exact Nash equilibria achieved under perfect information. On the other hand, if one now considers a ring type of a graph or a cycled communication, the dynamics behave like the way you see on the left. So the same steady state value, but completely different and obviously much slower because they actually have to do a lot more communication versus when the strength of the communication graph, that lambda 2 was higher. So this result that we have actually encapsulates the nice trade-off that you have between communication versus game properties. The second example that I want to show is this wireless ad hoc network where one has, I think there are only 15 users here, and each user decides its own rate through the path of the network. And there is a maximal capacity, and one has to adjust their rate so that they're minimizing their cost, and that cost is the negative of its utility function, that log type function, and then the price function that encapsulates that capacity constraint that one has. The communication graph that you see there, it's quite sparse. So what I'm going to show you are going to be results of simulation for the 3 types of discrete time algorithms this time. It's going to be the diminishing step size, that's the red one, constant step size, that's the black, and then the blue one is the ADMM one. And what you see is that the ADMM goes very quickly that's close to a steady state. The diminishing step size one, slowly, and then what you're going to see till the end is that the diminishing step size and the ADMM one get to a perfect convergence to the NE, while the constant step size, that original first algorithm that I showed you, still has that residual. It cannot deal with just reducing and completely removing that residual. So this is definitely showing the benefit of that correction factor. Finally, just this is a very, if you want, toy example, because I don't have 20 or 15. I only have 5 players. This is one what Fred, my PhD student, set up, and I asked him, can we have more? I don't think people have only 5 friends in their Facebook account. Nevertheless, this is what I have. But it is, why do I want to put it is because it's a network that's directed. Yeah? Up until now, everything was undirected. So I have a directed communication graph and a directed interference graph, in the sense that this GI includes attention drawn from the network, the attention that one gets from his friends. And we're going to assume that each has a strongly connected communication graph and receives whatever the friend that he's following in his news feed. So the idea of this game is one is trying to basically decide how much should I post so that I get the maximum attention But at the same time, keeping into account that I actually have some cost incurred when I'm doing that posting. So I have, first of all, a posting cost that I'm assuming it's linear in what I'm paying to produce this XI unit of information. And I have some payoff from the users that I follow because I receive whatever information. And then I have some attention from the network. It's an incrementally payoff that a user obtains from receiving attention in his network. Basically, this is a model that people have used. It's not ours. What we've used it for, we've used it to actually run our first algorithm with diminishing step sizes. And basically, we've recovered the results that they've obtained in the sense that we get to something that intuitively is telling 1, which makes intuitive sense. The players that have more followers get more attention. They get incentivized to produce more information. And in this way, get more benefit from actually using the network. So, in conclusion, I've talked about a few of the results that we've obtained, but there are a lot of others problems. And I hope that people realize that this is an area that's rife with challenges and interesting questions. First of all, how one gets from a Nash equilibria to a generalized Nash equilibria, in the sense when I do have couplings between the actions of my players. And it turns out that an operator theoretic approach is what actually allows one to develop in a very elegant manner such results. Because there, if you think that I'm actually going to put on top of dynamics or algorithms something else, it's complicating a lot. Well, an operating theoretic approach is slashing through a lot of that. It's very beautiful. We actually have an invited session at the next CDC with Sergio Grammatico, and I invite all of you to attend if you can. Then directed time-varying graphs. We only did directed graphs for diminishing step sizes, nothing for constant step sizes or continuous time. How do I reduce the memory or the processing requirement? Remember that I assume that everybody keeps the estimate of everybody else. That could be quite a lot. How do I actually relax that strong monotonicity in the partial information case? That's something that, again, it's a technical issue that seems quite tricky. How to deal with cheating players? The assumption was that in order to overcome the lack of global information, because there's no central node that tells them what the other ones are doing, they have to rely on what the others are telling them. What if they cheat? And this is a very important aspect. And then obviously the other classes, reinforcement learning. There at least I don't have to know what my opponents are doing. I don't have to necessarily know what my cost function looks like. I only have to record what my payoff is. And this is only some of them. Yeah?
Okay.
Thank you.
Thank you very much, Lacra. And we have time maybe for one quick question. Thank Lacra again.
Thank you. I don't know, wait, where you choose.